Hello, everyone. Welcome to SleepSpace. Tonight, we'll talk about something fundamental, something so deeply woven into the fabric of our reality that it touches every star, every atom, and even every thought. What is almost everything made of? As you settle in and allow your body to relax, let your mind drift through the cosmos with us. This journey will be scientific, gentle, and expansive, perfect for curiosity and for calm. Let's begin with a question that has echoed through human history. What is the universe made of? For centuries, people thought the answer was simple: earth, air, fire, and water. The ancient Greeks believed these four elements composed everything. These were poetic guesses, intuitive rather than tested. But they show how deeply we've always wanted to know what lies beneath the surface of reality. Over time, those four elements gave way to something more complex, something tested through observation and experiment. Today, the question still fascinates scientists, but now we have tools: telescopes, particle accelerators, quantum equations that help peel back the layers. If you zoom in on anything, your hand, your pillow, a mountain, or even a star, you'll eventually reach atoms. Atoms are the building blocks of matter. They are tiny, structured, and surprisingly empty. They consist of a dense core, the nucleus, surrounded by a cloud of electrons. This might seem like a solid object, but most of an atom is actually empty space. Imagine a grain of rice in the middle of a football stadium. That's the nucleus. The electrons would be tiny specks spinning around the outer stands. Everything between? Nothing. Just emptiness. Atoms are made of smaller particles still: protons, neutrons, and electrons. Protons and neutrons make up the nucleus. Electrons orbit the nucleus at vast distances. But what are protons and neutrons made of? This brings us to the strange and mysterious world of subatomic particles, quarks and gluons. Quarks come in different flavors, such as up, down, strange, and charm. Protons are made of two up quarks and one down quark. Neutrons have two downs and one up. These quarks are held together by gluons, the particles that carry the strong nuclear force. Gluons act like invisible threads, binding quarks together inside the nucleus. So if we look closer, protons and neutrons are not indivisible. They're made of quarks, held together by gluons, wrapped in a storm of energy. And electrons? Electrons are fundamental particles. As far as we know, they are not made of anything smaller. They simply are. Now, you might be wondering, are these particles everything? Is that what everything is made of? Surprisingly, no. Matter, the stuff we see and touch, makes up only about 5% of the known universe. The rest is far more mysterious. Around 27% is dark matter, and 68% is dark energy. We don't know exactly what dark matter is made of. It doesn't emit light, doesn't reflect it, doesn't absorb it. But we know it exists because of how galaxies spin. The stars at the edges of galaxies move faster than they should. Something invisible, something massive, must be holding them in. Dark energy is even stranger. It's not matter at all. It seems to be a property of space itself, a force that pushes galaxies apart, stretching the universe wider and wider. This acceleration of cosmic expansion was discovered in the late 1990s and remains one of the greatest mysteries in modern physics. But let's return to the 5%, the matter we can see and study. Everything in that sliver: stars, trees, oceans, planets, and people, is made from atoms. But not all atoms are created equal. The periodic table lists over 100 elements, from hydrogen to uranium. Each element has a different number of protons. Hydrogen, with 1 proton, is the lightest. Uranium, with 92 protons, is among the heaviest. These elements formed in different cosmic environments. The lightest, hydrogen and helium, were created moments after the Big Bang. Heavier elements were forged inside stars. In their fiery cores, stars smash hydrogen into helium through fusion. When they die in spectacular supernova explosions, stars create heavier elements, carbon, oxygen, iron, and scatter them across the galaxy. Every atom of iron in your blood, every atom of calcium in your bones, was born in a dying star. So what are we made of? Carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus. These 6 elements make up 99% of the human body. They arrange into molecules, cells, tissues, and consciousness. It's humbling to realize we are literally stardust, collections of atoms that once lit up the night sky. But there's another layer to reality beneath particles and atoms, a strange, mathematical world called quantum fields. In modern physics, particles aren't the smallest building blocks. They are excitations, little ripples, in invisible fields that fill the universe. Think of the surface of a calm lake. Drop a pebble in, and it makes ripples. In the same way, when energy moves through a quantum field, it creates a particle. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. This is quantum field theory, the most accurate model of reality we've ever built. According to this theory, everything is fields. Even the vacuum of space is not truly empty. It is seething with energy, full of virtual particles popping in and out of existence. The universe is a grand ocean of invisible fields, and matter is just the visible foam on the surface. If everything is made of quantum fields, then even the idea of a particle is a kind of illusion, a useful description for something deeper and more abstract. And what about energy? Is everything made of energy? In a sense, yes. Matter and energy are 2 sides of the same coin. Einstein's famous equation, E equals mc2, tells us that mass and energy are interchangeable. A small amount of mass contains a vast amount of energy. This is how nuclear power works, by converting tiny bits of mass into explosive amounts of energy. But not all energy has mass. Light, for example, has no rest mass, but it carries energy and momentum. A single photon can knock an electron free from an atom. So when we ask what everything is made of, we must include energy, massive and massless forms alike. Still, if you ask a physicist what really exists, they'll say fields. Particles, atoms, energy, these are behaviors of fields. These fields stretch across all space, interacting, vibrating, collapsing, evolving. They don't have color or shape. They're abstract. But their interactions give rise to everything we can see and touch. And then there's space-time itself, the stage on which all these particles and fields dance. Is space a thing? Is time a substance? Einstein showed us that space and time are woven together into a single fabric, bent and curved by mass and energy. Gravity is not a force pulling us down. It's the warping of space-time by the mass of the Earth. So is the space-time part of what everything is made of? Or is it the background? Some theories suggest space and time are emergent. that they arise from deeper quantum processes we don't fully understand yet. In those models, even the fabric of space might be made of something more basic. All this paints a stunning picture. The world isn't made of solid objects. It's made of fields and ripples, energy and probabilities, patterns and symmetries. What we see is the result of deeper, invisible processes. So when we ask what everything is made of, the answer depends on how deep you want to go. On one level, atoms. On a deeper level, quarks and electrons. Deeper still, quantum fields. And perhaps, beyond even that, something yet to be discovered. As you let this sink in, think about the air around you, the pillow beneath you, the quiet of the night. It's all made from atoms, which are made from particles, which are ripples and fields, which may be part of something more fundamental still. You are a collection of fields, vibrating softly in the stillness of space. The universe is not solid. It is structured, patterned, vibrating, more like music than machine. And you are part of that music, resting gently in its rhythm. Let's continue by exploring one of the most misunderstood ideas in modern science: quantum mechanics. If we want to truly understand what everything is made of, we need to understand the strange rules that govern the smallest scales of reality. At the quantum level, particles don't behave like tiny billiard balls. They behave more like waves, probabilities, and clouds of potential. An electron, for instance, isn't in one place until you measure it. Until then, it exists in a range of possibilities, a cloud of probability called a wave function. This is deeply different from our everyday experience. In our world, things are where they are. A book is on the table, a star is in the sky. But in the quantum world, objects have a fuzziness to them. They don't have a definite position or momentum until something interacts with them. This principle, known as the uncertainty principle, says that the more precisely you know a particle's position, the less precisely you know its momentum, and vice versa. So what is an electron really made of? Is it a wave, a particle, a field? In quantum mechanics, it is all of these things and none of them. It is a mathematical object described by its wave function. When you observe it, the wave function collapses and you get a specific outcome: a position, a momentum, a spin. But between measurements, it's just a cloud of potential. This leads to the idea that reality is fundamentally probabilistic. Not because we lack knowledge, but because reality itself is built that way. At the smallest scales, certainty dissolves into possibilities. And from those possibilities, everything we experience emerges. But quantum mechanics doesn't only apply to electrons and atoms, it applies to everything. It's just that for large objects, like people and planets, the quantum effects average out and the classical world appears. But beneath the surface, quantum rules still apply. So when we ask what everything is made of, we must also ask, what are these quantum fields and wave functions really made of? Are they real? Or are they simply tools for prediction? Physicists debate this. Some believe the wave function is just a mathematical device, a way to calculate outcomes. Others believe it is a real thing, a field of potential that exists until it collapses into reality. Either way, the wave function is one of the most powerful concepts in physics. It allows us to predict behaviors, build technologies, and understand the structure of atoms, molecules, and matter itself. Let's go even deeper. We know particles interact with each other through forces. These forces, like gravity, electromagnetism, and the nuclear forces, are carried by particles called force carriers. For example, The electromagnetic force is carried by photons. The strong nuclear force is carried by gluons. The weak force, responsible for radioactive decay, is carried by W and Z bosons. And gravity? That one remains a mystery. In theory, it should be carried by a particle called the graviton, but we've never observed it. All these particles, quarks, electrons, photons, gluons, are part of the standard model of particle physics. This is our best theory of the fundamental ingredients of matter. It's like the periodic table of particles, categorizing everything we've discovered so far. The standard model explains the behavior of 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity remains outside the standard model, stubbornly separate. According to the standard model, there are 17 fundamental particles: 6 quarks, 6 leptons, 4 force carriers, and 1 special particle: the Higgs boson. The Higgs boson deserves a closer look. For decades, physicists wondered why some particles have mass and others don't. The Higgs field was proposed to explain this. It is an invisible field that fills all of space. As particles move through it, they interact with it, and this interaction gives them mass. The stronger the interaction, the more mass they gain. Particles like photons don't interact with the Higgs field, so they remain massless. Others, like the W and Z bosons, interact strongly and gain mass. The Higgs boson is the quantum ripple in the Higgs field. It was famously discovered in 2012 at the Large Hadron Collider, confirming a key part of the standard model. Without the Higgs field, everything would move at the speed of light, and matter as we know it couldn't exist. So, what is almost everything made of? At this level, the answer seems to be a small family of particles interacting through force-carrying bosons, shaped by quantum fields, guided by probabilities. These particles include quarks, which make up protons and neutrons, and leptons, which include electrons and neutrinos. They interact via the electromagnetic force, the strong nuclear force, and the weak force. And they get their mass from the Higgs field. It's an elegant structure, but it's also incomplete. Let's take a moment to talk about the role of symmetry in this structure. In physics, symmetry is not just beauty, it's power. Many laws of nature are governed by symmetry principles. For example, the conservation of energy is linked to the symmetry of time. The conservation of momentum comes from spatial symmetry. The standard model itself is built on symmetry groups, mathematical patterns that describe how particles transform and interact. These symmetries are like the blueprint for the universe's behavior. They define how particles behave, what forces exist, and how everything interacts. But here's the strange part. When these symmetries break, the universe changes. This is called symmetry breaking, and it's not a flaw, it's essential. The Higgs field, for example, breaks a symmetry that existed in the early universe. When the universe cooled, this symmetry broke, and particles gained mass. Without broken symmetry, there would be no structure, no atoms, no galaxies, no life. This delicate balance, perfect symmetry, broken in just the right way, is what makes the world possible. Now, let's return to dark matter. Dark matter does not fit into the standard model. We know it's there. Its gravity shapes galaxies and clusters, but we don't know what it's made of. It could be made of particles that are invisible to our detectors. Some theories propose WIMPs, weakly interacting massive particles. Others suggest axions or sterile neutrinos. These particles, if they exist, would be part of a new sector of physics, a shadow realm of matter that interacts with ours only through gravity. Finding them would mean discovering a whole new family of building blocks. And dark energy? That's even more mysterious. It's not matter at all. It seems to be a property of empty space, a kind of pressure that pushes galaxies apart. It might be linked to the energy of the vacuum, to quantum fluctuations, or to something we haven't even imagined yet. In this context, the visible world, the stars, planets, atoms, and people, is just a thin layer, like the foam on a deep, invisible ocean. Let's also consider the role of fields in the early universe. Right after the Big Bang, the universe was a hot, dense soup of energy. There were no atoms, no stars, just fields interacting wildly. As it cooled, particles emerged, forces separated, and matter took shape. This period is known as cosmic inflation, a rapid expansion that stretched space-time and set the stage for galaxies and planets to form. In that early universe, quantum fields didn't just describe matter, they were reality. The fluctuations in those fields seeded the structure of everything to come. Tiny ripples grew into galaxies, and from those galaxies, stars formed. And from those stars, heavier elements. And from those elements, us. So when we ask what everything is made of, we are asking what gave birth to all structure, all form, all light and shadow. The answer, again and again, seems to be fields. Invisible, fluctuating, dynamic fields. And yet, there may be more beneath them. Some theories suggest that even quantum fields are not the deepest layer. String theory proposes that all particles are not points, but tiny vibrating strings. The different vibrations create different particles, just as different tones emerge from a plucked string. In this view, everything, quarks, photons, even gravity, is made from tiny loops of energy vibrating in extra dimensions of space. These extra dimensions might be curled up, hidden from view, but they could explain why we have the particles and forces we do. They could unify all physics, including gravity, with a single framework. Other theories go further still, suggesting that information, not matter, is the most fundamental substance. That space, time, and particles all emerge from patterns of information, processed by the universe itself. It's a radical idea, but it's gaining attention. Because in the end, the question of what everything is made of isn't just a scientific one, it's a philosophical one. We're peeling back the layers of the universe, looking for the foundation. But the deeper we go, the more abstract the foundation becomes. And maybe that's the beauty of it. Maybe the universe isn't made of things, but of relationships, of interactions, of energy shaped by form, and form shaped by energy. You are part of this great pattern. Your body is made of atoms forged in stars, built from particles formed in the first seconds of the universe. Your thoughts arise from electric signals in neurons, which are built from molecules, built from atoms, built from fields. So when you look around at the stars, the sky, the gentle darkness, you are seeing echoes of the same origin. You are not separate from the universe. You are its expression. Everything is made of the same fabric. And that fabric, at its deepest level, may be something we are only just beginning to understand. Let's continue by exploring one of the most misunderstood ideas in modern science: quantum mechanics. If we want to truly understand what everything is made of, we need to understand the strange rules that govern the smallest scales of reality. At the quantum level, particles don't behave like tiny billiard balls. They behave more like waves, probabilities, and clouds of potential. An electron, for instance, isn't in one place until you measure it. Until then, it exists in a range of possibilities, a cloud of probability called a wave function. This is deeply different from our everyday experience. In our world, things are where they are. A book is on the table, a star is in the sky. But in the quantum world, objects have a fuzziness to them. They don't have a definite position or momentum until something interacts with them. This principle, known as the uncertainty principle, says that the more precisely you know a particle's position, the less precisely you know its momentum, and vice versa. So what is an electron really made of? Is it a wave, a particle, a field? In quantum mechanics, it is all of these things and none of them. It is a mathematical object described by its wave function. When you observe it, the wave function collapses and you get a specific outcome, a position, a momentum, a spin. But between measurements, it's just a cloud of potential. This leads to the idea that reality is fundamentally probabilistic. Not because we lack knowledge, but because reality itself is built that way. At the smallest scales, certainty dissolves into possibilities. And from those possibilities, everything we experience emerges. But quantum mechanics doesn't only apply to electrons and atoms. It applies to everything. It's just that for large objects, like people and planets, the quantum effects average out, and the classical world appears. But beneath the surface, quantum rules still apply. So when we ask what everything is made of, we must also ask, what are these quantum fields and wave functions really made of? Are they real? Or are they simply tools for prediction? Physicists debate this. Some believe the wave function is just a mathematical device, a way to calculate outcomes. Others believe it is a real thing, a field of potential that exists until it collapses into reality. Either way, the wave function is one of the most powerful concepts in physics. It allows us to predict behaviors, build technologies, and understand the structure of atoms, molecules, and matter itself. Let's go even deeper. We know particles interact with each other through forces. These forces, like gravity, electromagnetism, and the nuclear forces, are carried by particles called force carriers. For example, the electromagnetic force is carried by photons. The strong nuclear force is carried by gluons. The weak force responsible for radioactive decay is carried by W and Z bosons. And gravity? That one remains a mystery. In theory, it should be carried by a particle called the graviton, but we've never observed it. All these particles, quarks, electrons, photons, gluons, are part of the standard model of particle physics. This is our best theory of the fundamental ingredients of matter. It's like the periodic table of particles, categorizing everything we've discovered so far. The standard model explains the behavior of 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity remains outside the standard model, stubbornly separate. According to the standard model, there are 17 fundamental particles, 6 quarks, 6 leptons, 4 force carriers, and 1 special particle, the Higgs boson. The Higgs boson deserves a closer look. For decades, physicists wondered why some particles have mass and others don't. The Higgs field was proposed to explain this. It is an invisible field that fills all of space. As particles move through it, they interact with it, and this interaction gives them mass. The stronger the interaction, the more mass they gain. Particles like photons don't interact with the Higgs field, so they remain massless. Others, like the W and Z bosons, interact strongly and gain mass. The Higgs boson is the quantum ripple in the Higgs field. It was famously discovered in 2012 at the Large Hadron Collider, confirming a key part of the Standard Model. Without the Higgs field, everything would move at the speed of light, and matter as we know it couldn't exist. So, what is almost everything made of? At this level, the answer seems to be a small family of particles interacting through force-carrying bosons, shaped by quantum fields, guided by probabilities. These particles include quarks, which make up protons and neutrons, and leptons, which include electrons and neutrinos. They interact via the electromagnetic force, the strong nuclear force, and the weak force. And they get their mass from the Higgs field. It's an elegant structure, but it's also incomplete. Let's take a moment to talk about the role of symmetry in this structure. In physics, symmetry is not just beauty, it's power. Many laws of nature are governed by symmetry principles. For example, the conservation of energy is linked to the symmetry of time. The conservation of momentum comes from spatial symmetry. The Standard Model itself is built on symmetry groups, mathematical patterns that describe how particles transform and interact. These symmetries are like the blueprint for the universe's behavior. They define how particles behave, what forces exist, and how everything interacts. But here's the strange part. When these symmetries break, the universe changes. This is called symmetry breaking, and it's not a flaw, it's essential. The Higgs field, for example, breaks the symmetries that existed in the early universe. When the universe cooled, this symmetry broke, and particles gained mass. Without broken symmetry, there would be no structure, no atoms, no galaxies, no life. This delicate balance, perfect symmetry, broken in just the right way, is what makes the world possible. Now, let's return to dark matter. Dark matter does not fit into the Standard Model. We know it's there. Its gravity shapes galaxies and clusters, but we don't know what it's made of. It could be made of particles that are invisible to our detectors. Some theories propose WIMPs, weakly interacting massive particles. Others suggest axions or sterile neutrinos. These particles, if they exist, would be part of a new sector of physics, a shadow realm of matter that interacts with ours only through gravity. Finding them would mean discovering a whole new family of building blocks. And dark energy? That's even more mysterious. It's not matter at all. It seems to be a property of empty space, a kind of pressure that pushes galaxies apart. It might be linked to the energy of the vacuum, to quantum fluctuations, or to something we haven't even imagined yet. In this context, the visible world, the stars, planets, atoms, and people, is just a thin layer, like the foam on a deep, invisible ocean. Let's also consider the role of fields in the early universe. Right after the Big Bang, the universe was a hot, dense soup of energy. There were no atoms, no stars, just fields interacting wildly. As it cooled, particles emerged, forces separated, and matter took shape. This period is known as cosmic inflation, a rapid expansion that stretched space-time and set the stage for galaxies and planets to form. In that early universe, quantum fields didn't just describe matter, they were reality. The fluctuations in those fields seeded the structure of everything to come. Tiny ripples grew into galaxies. And from those galaxies, stars formed. And from those stars, heavier elements. And from those elements, us. So when we ask what everything is made of, we are asking what gave birth to all structure, all form, all light and shadow. The answer, again and again, seems to be fields. Invisible, fluctuating, dynamic fields. And yet, there may be more beneath them. Some theories suggest that even quantum fields are not the deepest layer. String theory proposes that all particles are not points, but tiny vibrating strings. The different vibrations create different particles, just as different tones emerge from a plucked string. In this view, everything, quarks, photons, even gravity, is made from tiny loops of energy vibrating in extra dimensions of space. These extra dimensions might be curled up, hidden from view. But they could explain why we have the particles and forces we do. They could unify all physics, including gravity, with a single framework. Other theories go further still, suggesting that information, not matter, is the most fundamental substance, that space, time, and particles all emerge from patterns of information processed by the universe itself. It's a radical idea, but it's gaining attention. Because in the end, the question of what everything is made of isn't just a scientific one, it's a philosophical one. We're peeling back the layers of the universe, looking for the foundation. But the deeper we go, the more abstract the foundation becomes. And maybe that's the beauty of it. Maybe the universe isn't made of things, but of relationships, of interactions, of energy shaped by form and form shaped by energy. You are part of this great pattern. Your body is made of atoms forged in stars, built from particles formed in the first seconds of the universe. Your thoughts arise from electric signals in neurons, which are built from molecules, built from atoms, built from fields. So when you look around at the stars, the sky, the gentle darkness, you are seeing echoes of the same origin. You are not separate from the universe. You are its expression. Everything is made of the same fabric. And that fabric, at its deepest level, may be something we are only just beginning to understand. Let's explore more deeply what atoms truly are. On the surface, we often imagine atoms as miniature solar systems, a dense nucleus at the center with electrons orbiting around it like planets. This model, known as the Bohr model, is useful for basic explanations, but it doesn't capture the full quantum reality. In truth, electrons don't orbit the nucleus in neat circular paths. They exist in clouds of probability called orbitals. An orbital is not a path, but a region where an electron is likely to be found. These clouds come in distinct shapes: spheres, dumbbells, and more, each corresponding to a specific energy level. These patterns define how atoms interact, bond, and form the molecules that make up everything from water to DNA. The nucleus itself is tiny, about 100,000 times smaller than the atom, but contains nearly all of the atom's mass. Inside it are protons and neutrons, bound tightly together by the strong nuclear force. This force is so powerful that it overcomes the repulsive force between positively charged protons. Without it, atomic nuclei would fly apart instantly. Now, let's talk about quarks again, because the deeper we go, the more important they become. Protons and neutrons are each made of 3 quarks, but quarks are never found alone in nature. They are always confined inside larger particles, a phenomenon called quark confinement. It's as if the universe doesn't allow quarks to be alone. The force between quarks, carried by gluons, actually becomes stronger as they move apart, unlike most forces that weaken with distance. This is why quarks are permanently bound into larger particles. This idea that even the smallest pieces have internal structure is one of the most profound discoveries in physics. It suggests that what appears simple and indivisible often contains layers of hidden complexity. But we also need to ask, where do these particles come from? What governs their behavior? Enter the laws of quantum mechanics and the framework of quantum field theory. According to quantum field theory, each type of particle is an excitation of its corresponding field. The electron field, the quark fields, the photon field, they all fill space. A particle is just a bump, a ripple, a tiny bit of energy vibrating in one of these invisible fields. These fields are not static. They are dynamic, constantly fluctuating. Even in a perfect vacuum, where no particles are supposed to exist, quantum fields never truly rest. They jitter with uncertainty. These fluctuations can momentarily create pairs of particles and antiparticles that appear and then annihilate each other. These virtual particles are short-lived and unobservable directly, but they influence the behavior of real particles in measurable ways. One famous example of this is the Casimir effect. If you place two metal plates very close together in a vacuum, they will feel a force pulling them together, not because of gravity or magnetism, but because the quantum fields between the plates behave differently than those outside. The vacuum itself has energy, and this difference in energy creates a measurable force. It's a striking reminder that even nothing, emptiness, is not truly empty. Another key idea is that particles and antiparticles exist in pairs. For every type of matter particle, there is an opposite, an antimatter counterpart. The electron has the positron, the proton has the antiproton. When matter and antimatter meet, they annihilate in a burst of pure energy. This leads to one of the deepest mysteries in cosmology. Why does our universe contain so much more matter than antimatter? According to our best theories, the Big Bang should have created equal amounts of both. But somehow, matter won out. This imbalance, called baryon asymmetry, is still not fully understood. It may be the reason why stars, planets, and people exist at all. Now let's shift focus to one of the most essential ingredients of reality: energy. Energy is not a substance, but a property. It's the capacity to do work or cause change. It appears in many forms: kinetic, potential, thermal, electrical, nuclear. But at the deepest level, energy is what allows fields to ripple, particles to move, and structures to form. Energy is also conserved. It cannot be created or destroyed, only transformed. This conservation law is one of the cornerstones of physics. It means that the total amount of energy in a closed system remains constant, even as it changes form. This leads us to the most famous equation in science, Einstein's E, mc2. It tells us that energy and mass are interchangeable. A tiny bit of mass contains a vast amount of energy. This is the principle behind nuclear reactions, where a small loss of mass results in huge energy release. It's also why stars shine, converting mass into energy through fusion. Let's return for a moment to electrons. These tiny, fundamental particles are responsible for so much of the structure and function of matter. They orbit atomic nuclei, form chemical bonds, and carry electric current. Despite their importance, they are incredibly light and small. They have no known internal structure. They appear to be point-like, with no size. They have charge, mass, spin, and interact with electromagnetic and weak forces. Spin, by the way, is a quantum property that doesn't correspond to spinning in space as we know it. It's more like an intrinsic angular momentum. Electrons have a spin of 1/2, making them fermions, particles that obey the Pauli exclusion principle. This principle states that no two fermions can occupy the same quantum state. This is why electrons stack into different orbitals in atoms, giving matter its structure. Bosons, on the other hand, like photons and gluons, can share states freely. They are force carriers. Without them, particles would never interact. So, we can start to group all known particles into two broad categories: fermions and bosons. Fermions make up matter. These include quarks and leptons. Bosons carry forces. These include the photon, electromagnetism, gluons, strong force, W and Z bosons, weak force, and the hypothetical graviton, gravity. The Higgs boson stands apart. It is unique in that it is associated with a field that gives mass to particles. It doesn't fit neatly into the other force categories. It's a mechanism, a field, a scaffold for mass. But even this beautiful structure, the Standard Model, has limits. It does not explain gravity. It does not account for dark matter. It does not unify the forces. And it cannot explain why the constants of nature have the values they do. For example, why does the electron have the mass it has? Why is the strength of the electromagnetic force what it is? These numbers appear arbitrary, but they are precise. If they were different by even a small amount, atoms wouldn't form, stars wouldn't burn, life wouldn't exist. Some physicists believe these constants are fixed by deeper laws yet to be discovered. Others propose the idea of a multiverse, an infinite collection of universes, each with different laws and constants. In that view, we live in a universe where the conditions happen to support life, because otherwise, we wouldn't be here to observe it. This is known as the anthropic principle. It's not a scientific explanation in the traditional sense, but it reminds us how mysterious the universe really is. Let's also talk about molecules, the next level of structure. When atoms bond together, they form molecules. The nature of those bonds depends on the arrangement of electrons. Covalent bonds involve shared electrons. Ionic bonds involve transferred electrons. Hydrogen bonds, while weaker, play a crucial role in biology, especially in the structure of DNA and proteins. These bonds arise from the electromagnetic force, the attraction between positively charged nuclei and negatively charged electrons. The patterns and shapes of molecules determine everything from the taste of food to the function of enzymes. Water, for instance, is a simple molecule, H2O, but its properties are extraordinary. It is a liquid over a wide temperature range. It has a high heat capacity. It expands when it freezes. These traits are critical for life. At the molecular level, chemistry emerges. And from chemistry, biology. The structure of carbon, with its ability to form 4 bonds, makes it the backbone of life. Carbon atoms form chains, rings, and complex shapes. They build sugars, fats, proteins, and nucleic acids. So from the tiniest quarks to the structure of molecules, everything is connected. The rules of quantum mechanics govern how atoms form. Those atoms shape molecules. Molecules form cells. Cells build bodies, and minds, and stories. All of this, every structure, every moment, arises from a handful of particles, fields, and forces. These invisible ingredients create the visible world, and they're not fixed in place. Atoms vibrate, molecules twist, electrons leap between energy levels. Even in solid matter, motion never truly stops. At absolute zero, the coldest possible temperature, all motion would cease. But even then, quantum fluctuations would remain. So even the most still object, a stone, a mountain, a whisper of dust, is alive with hidden motion, with the dance of particles and fields. The deeper we look, the more we see that solidity is an illusion. What appears still and firm is built from ripples in waves, from interactions that flash in and out of existence. What is almost everything made of? It's made of movement, of structure, of energy and form. It's made of laws, mathematical, invisible, yet universal. And you too are part of this fabric. Your body, your breath, your heartbeat, they are echoes of the same fundamental forces. Everything is connected. Everything is made of the same song. Let's now focus on a hidden but vital layer of reality, the vacuum. We often think of a vacuum as truly empty, a place devoid of matter, light, and motion. But in physics, the vacuum is far from empty. In fact, it may be the most active, dynamic environment in the universe. It's filled with invisible energy, subtle forces, and constant fluctuation. This concept arises from quantum field theory. According to it, even in the absence of particles, the fields that underlie everything continue to exist. They never rest. They vibrate faintly, generating what we call vacuum energy. This energy gives rise to phenomena like virtual particles, which constantly appear and disappear in the vacuum. These fleeting particles can't be directly observed, but they affect measurable reality. Their existence has been confirmed through effects like the Lamb shift, where the energy levels of electrons in hydrogen atoms are slightly altered by the vacuum around them. The vacuum, it turns out, pushes back against the particles that move through it. Then there's the zero-point energy, the lowest possible energy state a system can have. Even if you cool a field to absolute zero, it will still contain this zero-point energy. It's the natural jitter of existence. This means that true stillness, true emptiness, does not exist in our universe. In cosmology, the vacuum plays a central role in the evolution of space itself. As the universe expands, the energy of the vacuum doesn't seem to dilute. Instead, it persists. This may be why the expansion of the universe is accelerating, driven by what we call dark energy. Dark energy might be a property of the vacuum, an energy built into the structure of space-time itself. If so, then what we call nothing is actually the source of cosmic acceleration. It may even hold the key to the universe's ultimate fate. And speaking of fate, let's look at time, not as something we move through, but as something that emerges from the structure of the universe. In physics, time is often treated as a dimension, like space. But in quantum mechanics, time behaves differently. It flows in one direction, from past to future. But the fundamental equations of quantum physics are time-symmetric. They work just as well in reverse. So where does the arrow of time come from? Many scientists believe it comes from entropy, the tendency for systems to move from order to disorder. The second law of thermodynamics states that entropy always increases in a closed system. This creates the arrow of time. Eggs don't unscramble, stars don't unshine, memories don't reverse. But on the quantum level, particles don't experience time the same way we do. Their behavior is governed by probabilities and symmetries, not by clocks and calendars. This suggests that time, like mass or charge, may not be a fundamental property. It may emerge from deeper processes, perhaps from entanglement, or from the geometry of space-time. Some physicists even argue that time is not real in the way we think, that it's a construct, a way our minds interpret change. Let's return now to the idea of fields. There are many types of fields in physics. Each fundamental particle has a field: the electron field, the quark fields, the Higgs field. Then there are force fields: the electromagnetic field, the gravitational field, the gluon field. These fields interact, overlap, and influence one another. They are not passive. They respond to energy and matter. When a charged particle enters a region of space, it changes the local field. Other particles then respond to that change. In this way, everything influences everything else. The fields are woven together into a dynamic tapestry. You can't touch one thread without affecting the rest. And that brings us to one of the most surprising discoveries in physics: entanglement. Quantum entanglement occurs when two particles become linked in such a way that their states are no longer independent. Measure one, and you instantly know the state of the other, no matter how far apart they are. This connection is not a transmission of information. It's a shared state. The two particles are part of the same quantum system. Einstein called this spooky action at a distance, but it has been confirmed in countless experiments. Entanglement is real. It suggests that the fabric of the universe is deeply interconnected. That separateness is an illusion. Some researchers believe that space itself may emerge from entanglement, that the geometry of space-time is built from networks of entangled particles. This is a radical idea, but one with growing support. If true, then space isn't just a container for matter. It's a product of relationships between quantum states. Reality is not made of things. It's made of connections. Let's shift now to symmetry and conservation, two ideas that guide much of modern physics. Symmetries are patterns that stay the same when you change your perspective. For example, a sphere looks the same from every angle. That's rotational symmetry. A snowflake looks the same after a 60-degree turn. That's discrete symmetry. In physics, symmetries are tied to conservation laws. This connection was formalized by Emmy Noether, one of the most brilliant mathematicians in history. Her theorem states that every symmetry in nature corresponds to a conserved quantity. Time symmetry leads to conservation of energy. Space symmetry leads to conservation of momentum. Rotational symmetry leads to conservation of angular momentum. These conservation laws are not optional. They are woven into the structure of reality. They help explain why particles behave the way they do, why forces are predictable, and why the universe has order. But sometimes, symmetries break. And when they do, new phenomena emerge. In the early universe, the fundamental forces were unified. But as the universe cooled, symmetries broke, and the forces split into distinct interactions. This process is called spontaneous symmetry breaking. It's the same process that gives particles mass through the Higgs field. The symmetry of the vacuum breaks, and a new structure arises. Mass is not something particles always had. It's something they gain through interaction. So what is everything made of? It's made of interactions, of fields that influence each other, of symmetries that guide behavior, and breakings that allow diversity. It's a world built not from solid stuff, but from dynamic relationships. Now, let's look at gravity, the oldest and most familiar force, but also the most mysterious. Newton described gravity as a force between masses. Einstein redefined it as the curvature of space-time. Mass tells space how to curve. Space tells matter how to move. But gravity is unlike the other forces. It's incredibly weak. A small magnet can lift a paperclip against the pull of the entire Earth. And, unlike the quantum forces, We don't have a complete quantum theory of gravity. Many physicists believe gravity must be quantum at some level. But attempts to merge general relativity with quantum mechanics have run into deep problems. One possibility is that gravity arises from something even more fundamental, like entropy or information. Some researchers propose that space-time and gravity emerge from the behavior of quantum systems. This is known as emergent gravity. It suggests that gravity is not a fundamental force, but a large-scale effect of deeper quantum rules. And once again, we see the same idea. What we think of as basic may actually be emergent. Fields, particles, space, time, even gravity may all arise from hidden patterns we don't yet fully understand. Let's go smaller once more, into strings. String theory proposes that all particles are not points, but tiny loops of vibrating energy. These strings are unimaginably small, on the order of the Planck length, a billionth of a trillionth of a trillionth of a meter. Each vibration corresponds to a different particle. A string vibrating one way appears as a photon. Another way, and it's a graviton. In this theory, everything, mass, charge, spin, is a result of how a string vibrates. String theory also requires extra dimensions. Not just the 3 of space and 1 of time, but as many as 10 or 11. These extra dimensions may be curled up tightly, hidden from observation. While string theory remains unproven, it offers a tantalizing glimpse of unity. A single type of object, a vibrating string, might explain all forces, all particles, all interactions. At the edge of all this is the idea of information. Some physicists now believe that information may be the most fundamental ingredient of reality. That particles and fields, space and time, are emergent properties of information systems. This idea is supported by studies of black holes. According to quantum theory, information cannot be destroyed. But when matter falls into a black hole, it seems to vanish. This leads to a paradox, one that may be resolved if information is somehow encoded on the surface of the black hole, not inside it. This leads to the holographic principle, the idea that the universe itself may be like a hologram, that the three-dimensional world we see may be a projection of information stored on a distant surface. It's a radical idea, but it fits a growing pattern. Again and again, we find that the universe is not made of solid things. It's made of patterns, interactions, vibrations, fields, probabilities, and maybe, at the very bottom, information. You too are part of that pattern. A web of molecules, shaped by atoms, shaped by fields, shaped by rules. And, beyond those rules, perhaps, lies something even more subtle. The hidden code of reality. Let's now widen our view from the micro to the macro, from the quantum building blocks to the grand scale of the cosmos. Because what everything is made of is not only a question of the very small, but also of how the very small scales up to create the structure of the universe itself. We often think of the universe as composed of galaxies, stars, and planets, discrete, separate objects floating in space. But when we zoom out far enough, a pattern emerges. Galaxies are not randomly scattered. They form vast filaments, sheets, and clusters, with great voids in between. This web-like structure is called the cosmic web, and it stretches across billions of light years. This web formed from tiny fluctuations in the quantum fields of the early universe. When the universe was only a fraction of a second old, random quantum ripples were stretched out by a brief but dramatic expansion called inflation. Over billions of years, gravity pulled matter into these slightly denser regions, forming stars, galaxies, and clusters. So the largest structures in the cosmos originated from quantum events smaller than atoms. The tiniest differences in energy density were amplified to cosmic proportions. This is a deep connection, linking the quantum with the cosmic. It reminds us that everything, from atoms to galaxies, is part of the same story. Now consider this. Most of the matter in galaxies is invisible. We've talked about dark matter, a mysterious form of matter that doesn't emit, absorb, or reflect light. But its presence is undeniable. Galaxies rotate in ways that can't be explained by visible matter alone. The stars at their edges move far faster than expected, as though an invisible halo of mass surrounds them. This is dark matter. We know that dark matter makes up about 27% of the universe's total energy content, while ordinary matter, everything made of atoms, is only about 5%. That means most of what the universe is made of is something we can't directly observe. But what is dark matter made of? Many candidates have been proposed. One is the WIMP, a weakly interacting massive particle. These particles would interact through gravity and possibly the weak nuclear force, but not with light. So far, WIMPs haven't been detected, but experiments continue. Another possibility is the axion, an extremely light, elusive particle that could exist in enormous numbers and contribute to dark matter's mass. Or perhaps dark matter is composed of something even stranger, particles that don't fit into the standard model at all. If we could identify dark matter, we would be adding a new chapter to the book of what everything is made of. Until then, it remains one of the great mysteries of modern physics. Even more perplexing is dark energy. Discovered in the 1990s, dark energy is the name we give to the force causing the expansion of the universe to accelerate. This was unexpected. For most of history, scientists assumed gravity would gradually slow the expansion. But observations of distant supernovae showed the opposite. The universe is not just expanding, it's expanding faster and faster. Dark energy makes up about 68% of the universe's energy content. Yet, we know almost nothing about it. Is it a property of space itself? A new kind of field? A temporary phase? Some theories suggest it's related to the cosmological constant, a term Einstein once added to his equations to keep the universe static. He later called it his greatest blunder, but it may have been more prescient than he realized. The cosmological constant represents the energy density of empty space. If the vacuum contains energy, as quantum field theory suggests, then that energy could drive cosmic acceleration. But the numbers don't match. The theoretical prediction for vacuum energy is many orders of magnitude larger than what we observe. This mismatch is called the cosmological constant problem. And it's one of the biggest unsolved puzzles in physics. So we're left with a striking realization. Most of what the universe is made of is unknown. The atoms that make up stars, planets, and people, protons, neutrons, electrons, account for a mere sliver of reality. The rest is dark matter and dark energy, unseen, unmeasured, but deeply influential. This changes our perspective. What we experience as solid and visible is the exception, not the rule. Our bodies, our world, our senses, all are built on a tiny fraction of the universe's ingredients. And yet, that fraction is extraordinary. Let's dive back into that 5%, the world of baryonic matter, which includes everything we can touch, taste, and see. As we've explored, this matter is built from atoms, protons, neutrons, and electrons. But even within this 5%, most of the mass doesn't come from the particles themselves. It comes from the energy that binds them. Protons and neutrons are made of quarks, but the quarks contribute only a small part of their mass. Most of the mass comes from the strong nuclear force, specifically from the energy of the gluons that bind the quarks together. This is mass arising not from substance, but from interaction. It's a profound insight. Mass, as we understand it, is not just the sum of the parts. It's the result of relationships, forces, motion, and energy. Matter, in a real sense, is frozen energy. Einstein's equation, E equals mc2, reminds us that mass and energy are interchangeable. A small amount of mass contains a tremendous amount of energy. This principle powers stars, fuels nuclear reactions, and shows up in particle accelerators where energy is converted into new particles. When particles collide at high speeds, like in the Large Hadron Collider, they can create entirely new forms of matter. This mirrors the conditions of the early universe, when temperatures were so high that particles constantly transformed into one another. Understanding these collisions helps us understand how the universe evolved from pure energy into structured matter. Let's also consider the neutrino, one of the most ghostly particles in nature. Neutrinos are incredibly light, neutral particles that hardly interact with anything. Trillions pass through your body every second without leaving a trace. They are produced in nuclear reactions, in the sun, in supernovae, in particle decays. Despite their abundance, they are notoriously difficult to detect. And yet, they may hold clues to the early universe, to the behavior of matter, and even to why the universe contains more matter than antimatter. In recent years, experiments have shown that neutrinos have mass, though extremely small. This discovery reshaped our understanding of particle physics. The standard model had to be revised to account for it. This highlights an important truth. Our understanding of what everything is made of is not finished. The more we observe, the more we find exceptions, surprises, and unexplained phenomena. Let's pause here to reflect on the nature of observation. In quantum physics, measurement plays a central role. The act of observing a system, say, measuring an electron's position, changes its state. Before measurement, it exists as a cloud of probabilities. Afterward, it takes on a definite value. This is called wave function collapse, and it remains one of the most debated aspects of quantum mechanics. Does the universe require observers to take shape? Or is observation just another interaction, no different from a photon bouncing off a mirror? No one knows for certain. But this mystery points to something deeper. The idea that reality is not a fixed thing, but a process. Things don't simply exist, they emerge. They unfold. They become. This is especially true when we consider the nature of emergence, the process by which complex systems arise from simple rules. For example, the brain is made of neurons, cells that fire electrical signals. But consciousness, thought, and memory emerge from the interactions of these cells. Similarly, the behavior of gases, crystals, and even galaxies arises from simpler parts following basic laws. Emergence shows us that the whole can be more than the sum of its parts. That structure, pattern, and meaning can arise from seemingly random beginnings. And this is perhaps the most beautiful idea of all. That the universe, with all its stars and storms and songs, emerges from just a few ingredients. That almost everything is made of the same things. arranged in infinitely different ways. Atoms become cells, cells become organs, organs become minds. Minds write poetry, build telescopes, and ask what everything is made of. And the answer? It's not just particles, not just fields, not just energy or mass. It's patterns, relationships, interactions. It's the dance of forces and the play of probabilities. It's the echo of the Big Bang still ringing through space. It's the quiet hum of quantum fields beneath the surface of reality. Everything you've ever touched, seen, or imagined is built from this. Now, let's explore something even more fundamental than particles, fields, or forces. Let's ask, what does it really mean for something to exist? This question takes us deep into the realm of ontology, the philosophical study of being. Physics gives us the tools to describe how things behave, how they interact, and what they're made of. But beneath that, we must ask, what makes something real? Is a particle real if it cannot be directly observed? Is a field real if it exists only as a mathematical function? Is space itself real, or just a stage upon which matter moves? In modern physics, many things we once thought of as things have become relationships. For example, a particle is no longer a tiny speck of matter with definite properties. It is an excitation of a field, with properties that only take on specific values when measured. This leads us into the strange and beautiful world of quantum reality. Quantum mechanics tells us that reality is not deterministic. Instead, it is probabilistic. The future is not fully determined by the present. Instead, it is shaped by probabilities, by what might happen, not what must happen. This isn't because of ignorance or lack of knowledge, it's because the universe itself is built that way. The very nature of particles, energy, and even space-time is inherently uncertain. And yet, from that uncertainty, stable structures emerge. Atoms form, molecules combine, stars ignite, life evolves. We live in a universe that is both uncertain and reliable, random and structured, probabilistic at its core, yet capable of giving rise to the predictable rhythms of day and night, the tides, and the beating of the heart. How does this happen? One clue lies in the concept of decoherence. In quantum mechanics, particles exist in a superposition, a blend of possible states. But when a system interacts with its environment, it loses coherence. The superposition breaks down, and the system takes on a definite state. This is called decoherence. It's not quite the same as wave function collapse, but it helps explain why we don't see quantum weirdness in everyday life. Decoherence turns quantum possibilities into classical realities. It's how the fuzzy realm of atoms becomes the solid world of objects. And this leads us to the concept of emergent reality. Emergence is the process by which new properties arise from simpler parts. A flock of birds has patterns of movement that no single bird possesses. A brain has thoughts that no single neuron contains. A molecule has properties, like taste or scent, that no atom alone can explain. Reality, it seems, is layered. At the bottom are the quantum fields and particles, formless, probabilistic, and subtle. Above that are atoms, structured, defined by rules and symmetries. Then molecules, combinations of atoms with emergent behaviors. Then life, organized systems of molecules capable of reproduction, adaptation, and awareness. And finally, consciousness, a phenomenon that emerges from life and reflects upon itself. So when we ask, What is everything made of? The answer depends on what level we're asking about. At the deepest level, everything is made of fields, continuous, invisible, and fluctuating. At the human level, everything is made of experiences, shaped by perception, memory, and interpretation. Both are real, both are necessary, and both arise from the same cosmic ingredients. Let's go even deeper now, to the boundary of the known and the unknown. There is a scale in physics known as the Planck scale, the smallest scale at which space, time, and gravity can be meaningfully defined. Below this scale, about 1035 meters, our current understanding breaks down. Space may no longer be smooth, but instead frothy, fragmented, or pixelated. This idea has led some to propose that space-time is not continuous, but quantized. That there is a smallest possible unit of space and time. That the universe, like matter, is made of discrete building blocks. This is the basis of loop quantum gravity, a theory that attempts to unite general relativity with quantum mechanics. In this view, space is made of tiny loops woven into a network called a spin foam. Time, too, becomes an emergent property, arising from the interactions of these loops. This is not yet proven, but it offers a powerful idea that space, time, and gravity might emerge from something deeper. Let's step back and ask, why do we assume space is real at all? In Newtonian physics, space is absolute. It exists independently of the objects within it. In Einstein's relativity, space and time form a single fabric that curves in response to mass and energy. But in some modern theories, space is not a thing in itself. It is emergent, a consequence of information, entanglement, or deeper mathematical rules. One such idea comes from the ADIS-CFT correspondence, a concept in string theory. It proposes that a gravitational theory in a higher dimensional space, ADS, is equivalent to a non-gravitational theory on its lower dimensional boundary, CFT. In simple terms, it's as if a universe with gravity could be described entirely by a universe without gravity on its surface, like a hologram. This holographic principle challenges our most basic intuitions. It suggests that the three-dimensional world we see may be a projection of information stored in two dimensions. If this is true, then space, and possibly time, are not fundamental. They are illusions created by deeper structures. And what are those structures made of? Perhaps information. This brings us to the idea that information is the foundation of everything. In physics, information is more than data. It is a measure of possibilities. It defines the state of a system, the arrangement of particles, the configuration of fields. When something changes, information is transferred. When something is measured, information is gained. The laws of physics, in this view, are rules for how information evolves. Black hole thermodynamics supports this idea. A black hole's entropy, the measure of its hidden information, is proportional not to its volume, but to the area of its surface. This is deeply strange. It suggests that the information contained in a region of space is encoded on its boundary. Stephen Hawking showed that black holes can emit radiation, now known as Hawking radiation, and slowly evaporate. But if they evaporate entirely, what happens to the information inside? If it's lost, that would violate quantum theory, which says information is never destroyed. This paradox, called the black hole information paradox, is still unresolved. But it has led many physicists to believe that information, not matter or energy, is the most fundamental currency of the universe. In this framework, particles, fields, and even space-time emerge from informational processes. The universe becomes a quantum computer, processing bits and qubits of reality through interactions, measurements, and entanglement. This view is speculative, but it aligns with an ancient intuition that beneath the surface of the world lies something abstract. Not substance, but structure. Not objects, but patterns. Not things, but meaning. And maybe that's the ultimate answer. Maybe everything is made of meaning, encoded in the language of mathematics, expressed in the form of particles, fields, and forces, and interpreted through the lens of consciousness. You are part of this system. Your brain processes information. Your thoughts are patterns of electrical activity. Your memories are stored in the configuration of molecules. Your identity is not a substance. It is a process. So what is almost everything made of? It is made of fields, vibrations, and particles. It is made of interactions, forces, and symmetries. It is made of information processed over time. It is made of emergence, of simple parts forming complex wholes. It is made of the void and the dance of possibility within it. And perhaps it is made of wonder. Let's now turn our attention to something both ancient and modern. Light. Light, in many ways, is the bridge between the visible and the invisible. It carries information across vast distances. It reveals form, color, and texture. And yet, it is also a quantum object, full of paradox and mystery. So, what is light made of? Classically, light is described as a wave, an oscillation of electric and magnetic fields moving through space. This is the heart of electromagnetism, unified by James Clerk Maxwell in the 19th century. His equations showed that changing electric fields produce magnetic fields, and vice versa. When combined, they create a self-propagating wave, light. But in the early 20th century, experiments revealed that light also behaves like a particle. It can be emitted or absorbed in discrete packets of energy, called photons. This particle-like behavior was crucial in explaining the photoelectric effect, how light can knock electrons off a metal surface. This discovery earned Einstein the Nobel Prize. So which is it? Wave or particle? The answer is both, and neither. This is the wave-particle duality, one of quantum mechanics' most famous concepts. It tells us that light, and indeed all quantum objects, do not neatly fit into our classical categories. A photon is not a little bullet of light, nor a simple ripple in a field. It is a quantum excitation, a disturbance in the electromagnetic field that behaves like a wave in some contexts and like a particle in others. And light has no mass. It always travels at the same speed. The speed of light, about 272 kilometers per second in a vacuum. This speed is not just fast, it's fundamental. It's built into the fabric of space and time. In Einstein's theory of relativity, the speed of light is the cosmic speed limit. Nothing with mass can reach it, and nothing can exceed it. But photons are not just particles of light. They are the force carriers of electromagnetism. Every time two charged particles interact, they do so by exchanging photons. These photons are virtual. They don't exist as detectable particles, but they mediate the electromagnetic force. They're the messengers between electrons, the glue that holds atoms and molecules together. Without photons, there would be no chemistry, no biology, no vision, no light. And light isn't alone. The standard model includes other force carriers: gluons, which mediate the strong nuclear force, W and Z bosons, which govern the weak nuclear force, and, possibly, the graviton, a hypothetical particle that would carry the force of gravity, if gravity is indeed a quantum force. Each of these particles corresponds to a field, and each field fills the universe. These fields are not separate. They interact. The electromagnetic field can influence charged particles. The Higgs field gives mass to those particles. The quantum vacuum teems with fluctuations in all of these fields, a restless sea beneath the surface of apparent stillness. Let's pause to reflect on what this means. Everything is connected, not just in the poetic sense, but literally. You are immersed in fields. You are made of excitations of those fields. The space between your atoms is not empty. It is alive with potential, with the buzz of virtual particles and quantum foam. And yet, this invisible complexity gives rise to the solid, tangible world you know. Tables, trees, oceans, cities, everything you can touch is built from these patterns. Matter is not made of matter. It is made of relationships, interactions, dynamics. Let's revisit mass, a property we often take for granted. What gives an object its mass? Why does a proton weigh more than an electron? Why do some particles have mass and others do not? The answer lies in the Higgs field. The Higgs field is a scalar field that permeates the universe. Unlike other fields, it has a non-zero value even in its lowest energy state. This means that particles moving through the Higgs field interact with it, some more strongly than others. This interaction is what gives them mass. The photon does not interact with the Higgs field. It remains massless. The W and Z bosons interact strongly. They are massive. The electron interacts weakly, so it has a small mass. This process is not like objects being coated with substance. It's more like moving through a medium. Imagine a swimmer moving through water. The resistance they feel is like mass. The Higgs field creates resistance to acceleration. It gives particles inertia. In 2012, scientists at CERN discovered the Higgs boson, a particle associated with this field. Its detection was a major triumph, confirming a key part of the standard model. But it also opened new questions. Why does the Higgs field have the value it does? Could there be more than one Higgs? Does it connect to dark matter? We don't yet know, but we do know this. Without the Higgs field, particles would have no mass, atoms wouldn't form, stars wouldn't ignite, life wouldn't exist. So again, we see that reality is not made of things, but of fields, and of how those fields interact. And these interactions are governed by symmetries. Symmetry is a powerful idea in physics. It means that a system looks the same under certain transformations, like rotation, translation, or reflection. These symmetries are not just aesthetic, they imply conservation laws. As we saw earlier, Noether's theorem links symmetry with conservation. Time symmetry implies conservation of energy. Spatial symmetry implies conservation of momentum. Gauge symmetry, more abstract but essential, underlies the interactions of forces. The standard model is built on these gauge symmetries. It is a framework of stunning precision. It predicts the behavior of particles to extraordinary accuracy. But it's also incomplete. It doesn't explain gravity. It doesn't include dark matter. It doesn't predict the values of its own constants. And so physicists search for a deeper theory, a grand unified theory that would unite the electromagnetic, weak, and strong forces. Or even a theory of everything that would include gravity too. String theory is one candidate, loop quantum gravity is another. But no theory has yet succeeded. The answers remain elusive. In the meantime, we continue to explore, to measure, to build machines that collide particles at near light speed, revealing flashes of the early universe, to peer into space and see galaxies forming, stars dying, and light traveling across billions of years. Because every photon we catch tells a story. Every particle we detect is a clue. Every field we uncover adds a brushstroke to the portrait of reality. Let's now look again at the cosmic web. Galaxies are not isolated. They are connected by filaments of dark matter, strung like pearls on an invisible string. These filaments guide the motion of galaxies, the flow of gas, and the formation of stars. Simulations show that this structure, vast, interconnected, and beautiful, arises naturally from the laws of gravity acting on dark matter over billions of years. What begins as small quantum ripples in the early universe grows into galaxies, clusters, and superclusters. So the large-scale structure of the universe is yet another layer of emergence. Tiny quantum fluctuations become the scaffolding for cosmic architecture. And what about you? You are a structure too. You are made of atoms forged in stars. Those atoms form molecules, which form cells, which form thoughts. The same physical laws that govern galaxies govern you. You are not separate from the universe. You are part of its unfolding. A pattern, a process, a moment in time.